In this video, we'll be talking about exponential functions. Example 1 says, one day you are on a hike and you come across a genie, a magical being that grants you wishes. The genie says that you can have either option A, which is a lump sum of $1 million, or option B, which is a chessboard that has 1 cent on the first square, 2 cents on the second square, 4 cents on the third square, 8 cents on the fourth square, 16 cents on the fifth square, etc. A chessboard has 64 total squares. Which option do you decide to go with and why? So here we have a grid just to visualize the chessboard, and on the first grid we have 1 penny, 2 pennies, or 4 cents, and if you can see, the pattern is that each time we are doubling. Now, because there are 64 squares, it would take quite a long time to figure out how much money is on the squares. We could kind of just keep doubling, but there's got to be a more efficient way of going about doing this instead of just doubling this number a bunch of times. And that's where this new type of function comes in called an exponential function. So our goal here is to come up with a formula f of x that tells us how much money is on any given square x, where here we have square 1, 2, 3, 4, 5, 6, 7, 8. This would be square 9, square 10, etc. So let's see if we can't figure out a pattern that's appearing to help us come up with this exponential function. I know that if I plugged in 1 into my function, that would tell me how much money is on square 1, and that would be 1 cent or 1 penny. And if I wanted to figure out how much was on square 2, the way that we're going to get that is I'm going to take the previous amount and I'm going to double it, which this ends up equaling 0.02. The amount of money on the third square is going to be double the amount on the previous square. And so what I could do is I could just double that, but I'm going to write it in a way that it looks like this. Basically, I'm taking the previous amount, which was 0.01 times 2, and then I'm doubling that. And if we simplify that, that ends up being 0.04. Now for f of 4, I can take the previous amount, so I'm just going to copy this long form of this previous amount, and if I doubled that, then that would give us 8 cents, or $0.08. So could we write this in a way that is a little bit more compact instead of having to write a bunch of 2's? Because if I keep on going, I'm going to have to write out a lot of 2's. So the next one I'd have 1 cent times 2 times 2 times 2. So that would have represented the amount on the previous square, and I'm doubling that. And so that would end up giving me 0.16. So is there a way that we can condense repeated multiplication? And if you talked about using an exponent, you would be correct. So let's just do it with this last one that we had here. So I have 2 times 2 times 2 times 2. That is the same thing as 2 to the 4th power. So another way that I could write the value for f of 5 would be 0.01 times 2 to the 4th power. So that means that if I wanted to get the amount of money on the 6th square, I could write this as 0.01 times 2 to the 4th power times 2, and really I could condense that into a nicer form, or a more simplified form, as 0.01 times 2 to the 5th power. Let's do it one more time for f to the 7th power. This would be 0.01 times 2 to the 5th power times 2, which if I condense that, that would be 0.01 times 2 to the 6th power. Now, are you able to see a more generic way that we could do this based off what the input is and based off what our output is here? So basically, if I continued this on, for some general square f of x, or excuse me, for some general square x, then f of x, the amount of money on that square x, would be 0.01 times 2 to the power of, and then if you'll notice, the pattern is that whenever you have an input of something like 7, then the exponent is 6. When our input was 6, our exponent was 5. When our input was 5, our exponent was 4. So the exponent ends up being just one integer less than the input value, or the x value. So this would be x minus 1. And this represents our function that would help us find how much money is on a particular square. So now that we have this function that we came up with, we can utilize this to figure out how much money is on a particular square. Now, namely, I want to figure out how much is on the very last square because that's the square that's going to have the most amount of money on it. So if I wanted to figure this out using this formula, I could plug in 64 for x. So that would give us 0.01 times 2 to the power of 63. And if you throw this into your calculator, the number is so large that it ends up having to use scientific notation. So I'm going to round this to about 9.22 times 10 to the 16th power. So this number is so large that it has to use scientific notation. And the way that the 16 works is, if you're multiplying by a power of 10, because it's 10 to the 16th, that means that we would take our decimal place and we would move it to the right 16 places. And anytime we see a little space or a dip, we have to add a 0. So if I move this over 16 times, that would give us the number that would be on the 64th square. Now, as you can see, I haven't even moved over to the right 16 decimal places, and this is already a number that's much larger than $1 million. And this amount here, this amount of money, this long number, is just the amount of money that would be on the 64th square. So remember, you're taking that entire chessboard home with all of the money on it. So the fact that just the 64th square alone has that much money on it, it would be silly not to take option B instead of the lump sum of the $1 million. I know that if my brother were to encounter this situation and he chose the $1 million, I would be very upset with him. So there we have some of the math behind exponential functions, genies, and chessboards. Let's move on. So a function is an exponential function if it can be written in the form f of x equals a times b to the power of x, where a and b are real numbers and b has to be positive. Now, a has some different names, but sometimes you'll hear it called the starting value. And b also has some different names. Sometimes you'll hear it called the common ratio. And another thing that you'll hear b called is the growth factor. If b is greater than 1, then it's called a growth factor, because when we have an exponential function and the base b is positive and greater than 1, then it's called a growth factor and our output values are growing. If the b is greater than 0 but less than 1, then we will call it a decay factor, and we'll be dealing with something called exponential decay, which means that our output values are decreasing. So again, to reiterate, when our b value or our base is greater than 1, we have exponential growth, and then b is called a growth factor. If b is between 0 and 1, then we have exponential decay, and it is called a decay factor because our output values would be decreasing. Example 2 says, suppose a colony of bacteria in a petri dish has 700 cells at 1 p.m. Part A says, if the bacteria doubles every hour, how many bacteria cells will there be at 9 p.m. the same day? So just like last time, we want to create a function. I'll call this function f of x, and f of x is going to represent the number of bacteria cells after x number of hours. So if we're starting at 1 p.m. and ending at 9 p.m., that means that 8 hours will have elapsed. So again, f of x represents the number of bacteria after x number of hours. So f of x equals, we have a starting value. So remember a in our formula, A is referred to as the starting value. And so in this instance, our starting value is 700. That's how many cells we're starting off with. And then we know that it's doubling, so then our growth factor is going to be the value 2. And our exponent is just going to be x because it doubles every hour. So let's just kind of make sure that this function ends up working in terms of what we want it to do. So x would represent number of hours. And then f of x, so I'll put x here, and then f of x represents number of bacteria. So if 0 hours have elapsed, then we would plug in f of 0, and we'd have 700 times 2 to the power of 0. And when we raise that to the 0 power, that gives us 700 times 1, which is 700, which is what we were expecting because we are starting off with 700 bacteria cells. Let's try plugging in 1 now. So if I evaluated f of 1, we'd double 700 one time, and that's going to end up being 1400, which is again what we expected. And let's just try one more. If we did f of 2, that would be 700 times 2 squared, and that means we would be doubling it twice, and we'd get 2800, which is again what we're expecting. So now let's go ahead and answer the question that's being asked of us in part A. So if we plug in 8 into our function, we have f of 8, and I'm just going to throw that into a calculator, and that ends up giving me 179,200 bacteria cells at 9 p.m. So there's our answer for part A. All right, so now let's move on to part B, which says if the bacteria doubles every 3 hours, how many bacteria cells will there be at 9 p.m. the same day? So let's move on to part B. And since we're dealing with a new scenario, maybe I'll name this g of x. And we don't have quite the same scenario here, so let me erase these. We are still starting off with 700 bacteria cells at 1 p.m. And now what happens is it doubles every 3 hours. So my next row, my input value would be 3, and then it would double after an additional 3 hours. And then it would double again after 6 hours from the beginning. So we have that. And again, to reiterate, if we're at 9 p.m. and we're starting at 1 p.m., so 9 p.m. minus 1 p.m. gives us 8 hours. So the issue is that if I were to fill in another row in my table, if I put in 9 hours, then this would be at 5,600 cells. But 8 falls between 6 and 9 here. So our answer is going to be somewhere between 2,800 and 5,600 cells. But what value is that exactly? And because this doesn't grow linearly, we can't just use the idea of slope, because this is definitely not growing linearly. If I were to plot it, these would look, something like this, and it would grow in a fashion that looked something like that. So this is not linear, and we cannot use the idea of slope, which sometimes my students will, that's the conclusion that they'll jump to, is we can use the idea of slope, but we can't because this is not growing linearly. So we're going to need to once again create an exponential function. G of x equals, we're starting off with 700 cells. We are still doubling, but we're doubling every 3 hours. So what's going to happen is we're going to edit our exponent. So instead of it being x, it's going to be x divided by 3. So now if we were to plug in 3, it would double once. If we plugged in 6 for x, it would double twice, since 6 divided by 3 is 2. So now that we have this edited function, we can plug in 8, and that will tell us how many bacteria cells we'll have in this scenario after 8 hours. And if you throw this into your calculator, this ends up being approximately 4,444.72 bacteria cells. So there's our final answer for part B. Example 3 says sketch a graph of the functions f of x equals 2 to the power of x and g of x equals 2 to the power of negative x minus 3 and then plus 1. So let's start with f of x. If I plugged in 0, so f of 0 would equal 2 to the power of 0, which is equal to 1. That means that our y-intercept is going to be the point 0, 1. And then if I plugged in 1, that would be 2 to the power of 1, which would give us 2. And so what's going to happen is our output values are going to double each time. So if we have 2, then our next output value would be 4. And then our next output value would be 8. So 5, 6, 7, 8 would be right here. And unfortunately, 16 is getting kind of large and won't fit there. So it's going to look like this. And then let's see what happens when we plug in negative numbers. If I plugged in negative 1, I would have 2 to the negative 1 power. The way that negative exponents work is I could rewrite that as 1 over 2 to the positive 1 power, which is the same thing as 1/2. So if I plugged in negative 1, my output value would be 1/2. If I plugged in negative 2, I would have 2 to the negative 2 power, which is equal to 1 over 2 squared, and that simplifies to 1/4. So that's going to be about right here. And those output values are just going to keep getting smaller and smaller and smaller. And if you see the pattern moving to the left, the output values are getting cut in half. So here's kind of a paradoxical question. If you start out with a pound of cheese and you keep cutting it in half, will you ever run out of cheese? Well, realistically, you're going to get an amount so small that it's basically nothing, but mathematically, if you keep cutting a number in half, it's never actually going to reach 0. So what happens is it gets infinitely close to 0, but never touches 0. And so we've kind of explored this idea before. On our x-axis here, we have a horizontal asymptote. So there is a horizontal asymptote of y equals 0. So let's kind of talk about the end behavior of this function now. So as x approaches negative infinity, in other words, as we go to the left direction on the graph, the y values, f of x, those approach 0. And as x approaches positive infinity, those values go up, they keep increasing, and those go off to positive infinity. So this describes the end behavior of our graph here. And something else that I want to point out is whenever you have a function that's exponential and it looks like y equals a times b to the power of x, our a value is going to help us with our y-intercept. So our y-intercept is going to be the point 0, a. And it doesn't look like it, but f of x, we can rewrite it as 1 times 2 to the power of x. So this tells us that in this scenario, our y-intercept is the ordered pair 0, 1. I'm going to clean up the screen a little bit so that we can move on to graphing g of x. So one thing that I want you to be careful of is if you look at this function, the y-intercept is not going to be at 0, a, and it has to do with the fact that we are dealing with transformations in this graph, which we've learned about previously. And if you haven't, go back and watch those videos on transformations of functions. So just know that the y-intercept of this is not going to be 0, 1, and it has to do with the plus 1 on the end because we're dealing with a vertical shift. Also, it would probably be helpful to rewrite this as 2 to the power of negative x plus 3, like that. So I'm factoring out the negative in the exponent, and then we have plus 1. So now we can kind of talk about what do each of these things do. So this negative sign here is going to be a reflection over the y-axis because we're having negative 1 kind of be multiplied to the input value. So that means that we're reflecting over the y-axis. Then the plus 3 on the inside of the parentheses, that is a shift left 3 units. And then the plus 1 on the outside, that is a shift up 1 unit. So since the shift up 1 unit occurs, that's the only thing that's really affecting the horizontal asymptote. So what that tells us is that we are going to have a horizontal asymptote shifted up 1 unit from the parent graph, which we have graphed on the left. So here we have our horizontal asymptote, and it's the equation y equals 1. So I went ahead and I plotted some points and finished off the graph that shows the different transformations that happened. We had the reflection over the y-axis, the shift left 3 units, and the shift up 1 unit. So here is the graph. Let's go ahead and describe the end behavior now. So as x approaches negative infinity, then we have g of x, our output values, go off to positive infinity. As x approaches positive infinity, g of x approaches our horizontal asymptote. So we have g of x approaches the value 1. Example 4 says, use the table below to find a formula for the equations of f of x, g of x, and h of x. So we have this table here, and we want to come up with function formulas for each of the 3 functions that were given. Now, given that we are in the section of exponential functions, we might think that all of these are going to be exponential functions. But let's look at the first function. The output values are 4, 6.5, 9, 11.5, 14, 16.5, and 19. Do you notice a pattern? Pause the video and see if you can come up with functions for each of these, and then we'll go over them. So the pattern in the first row for f of x is that the output values are increasing at a constant rate. They are increasing by 2.5. So that should be a clue that f of x is not going to be an exponential function, but in fact a linear function. So f of x is equal to, I know that the slope is 2.5, and then we have x, and then we have plus whatever our b value is. And the way that we get b is it's the value that we get as an output when we plug in 0 into our function. So here it tells us that f of 0 is equal to 4, so that means that our b value is 4 here. Okay, let's move on to g of x. Do you notice a pattern in g of x? Well, the pattern is the output values are getting cut in half each time. So we're starting with 200, then it goes to 100, 50, 25, 12.5. So that means that g of x is an exponential function because each time we're multiplying the output by the same value. In other words, our common ratio. So we're starting with 200 because g of 0 is 200. And then our common ratio in this case is 1/2. And remember, we said earlier that when our common ratio is between 0 and 1, we have a decay factor and we have exponential decay, which means that our output values are decreasing. And then our exponent on this is going to be x. So there's our exponential function for g of x. H of x is also going to be an exponential function because going from 7 to 21, we're multiplying by 3. Then from here, we're multiplying by 3, multiplying by 3. So that's the pattern. Our common ratio is 3 here, and we're starting off with 7. Our growth factor is 3, and then our exponent is the input variable x. So this concludes example 4. Now we're going to start to talk about interest. Example 5 says, suppose you deposit $8,000 in a bank account that pays you 5% annual interest. Assume that the bank pays interest once per year at the end of the year, and that you place the interest under your bed for safekeeping. How much money will you have at the end of 2 years? So let's kind of see what ends up happening. We start off with $8,000, and if I were to take 5% of that, I want to multiply by 0.05. And that's going to end up being equal to $400. So what you're doing now is you're taking that $400 and putting it under your mattress. That's probably not a good idea and not a great place to hide your money, but that's what we're doing. So at the end of the first year, we have $8,400, but again, you're taking this $400, which represents your interest, and you're putting it under your mattress. So when the next year rolls around, we're once again going to calculate 5% of that $8,000 that you have. and that's again going to be $400. So in total, at the end of 2 years, you will have $8,000 plus 400 plus 400, and that's going to equal $8,800. So there's our answer for part A. For part B, it asks how much money will we have at the end of t years? So as you can see, this represents a linear function because every year you're gaining $400, which is the 5% of that initial amount of money that you put in, which was the $8,000. So if I wanted to create a function out of this, the amount that you would have at the end of t years would be 8,000 plus 400 times the number of years that pass. So this, I should probably put dollars. This represents how much money you'll have if you follow this scenario at the end of t years. So let's define what simple interest is. When interest is only paid on the original, which is another way of saying the principal amount of money, this is referred to as simple interest. If interest is paid once per year at an annual interest rate R with no interest paid on the interest, then after t years, an initial amount P, remember P stands for principal amount, grows to P times 1 plus RT. Let's show that this is the same thing that we got previously. So in this case, our P value would have been 8,000. So I have P times 1 plus RT. And then we have 1 plus R was our interest rate as a decimal. So that'd be 0.05. And then T is the number of years. So do we end up getting the same formula that we got in the box up above? Well, if I distribute in that 8,000, 8,000 times 1 is just 8,000. And then 8,000 times 0.05 is 400, and then we have t. So it does end up working, and here is the simple interest formula, which again is modeled by a linear function. But we're on the section about exponential functions, so maybe let's see how exponential functions play a role when we're talking about interest. Example 6 says, suppose you deposit $8,000 in a bank account that pays 5% annual interest. Assume that the bank pays interest once per year at the end of the year, and that you place that interest back into your account. How much money will you have after part A says 1 year, part B says 2 years, and part C says t years? So let's do the first calculation. We're starting off with $8,000. We want to calculate 5% of that, and then we're going to add that to our initial amount. So this ends up equaling 8,000 plus 400, which is equal to $8,400. Now, the difference between this scenario and the scenario above is that you're taking the interest that you earned, which was $400, and you're putting it back into your bank account so that the next time you get interest at the end of the year, you are now getting interest on a larger amount of money. So after 2 years, you now have $8,400. So if I calculated 5% of $8,400, this is going to end up equaling $420. So the total amount of money that you're going to have at the end of 2 years is going to end up being $8,400 plus the interest that you earned, which was $420. And so now this is $8,820. So notice if we do a comparison, in this scenario that we're describing, after 2 years we earn $8,820. And in the example where we were gaining simple interest, we got $8,800 at the end of 2 years. So that is a $20 difference, which doesn't seem like a lot, but if you compound over several years, it ends up making a huge difference. So that's what's happening here. What about after t years? How much money will we have? Let's try to figure that out. Let's come back up to this calculation that we did right here. What we did was we took our principal amount and added on the 5% of our principal amount. Another way that we could have calculated this is we have two terms, and both of our terms there have the number 8,000. So what if I factored 8,000 out of that expression? What would be left? Well, 8,000 divided by 8,000 is 1, and then if I divided that second term by 8,000, I would be left with 0.05. So if I simplified what's inside my parentheses now, this would be 8,000 times 1.05. So it turns out in this example, if you're increasing an amount by 5% each time, then our common ratio is 1.05. And instead of adding like that, we could just keep multiplying by 1.05 and it'll give you the output value that we are looking for. So it turns out that if you did 8,820 divided by 8,400, that would give you the number 1.05. And you can kind of test this out to see, but that's our common ratio. So let's go ahead and erase this and come up with an expression that represents how much we'll have after t years. So that will be, I'll put a $sign, 8,000 times 1.05 to the power of t. And that will represent our answer for part C. This is an exponential function. And recall here that because our common ratio is greater than the number 1, then we have exponential growth. And if it's smaller than 1 and greater than 0, then we have exponential decay. Example 7 says, suppose you deposit $8,000 in a bank account that pays 5% annual interest compounded twice per year. How much money will you have at the end of 1 year? So this works a little bit differently. Because we're compounding twice per year, basically we have the first 6 months and then the second 6 months, or the second half of the year. So after the first 6 months, what will happen is you'll have $8,000, and the amount of interest that you'll get on it is, since 5% represents our annual interest rate, we have to cut that in half. So we're getting 2.5%, which as a decimal is 0.025. And then if we add that to 8,000, this ends up equaling $8,200. So that's how much we'll have basically after the first 6 months, but we want to know how much money we'll have at the end of 1 year. So now we have to go and think about our second 6-month period. But now we have $8,200 in this scenario, or at this point in time, and then we're going to also calculate 2.5%. and then add that back to 8,200. And then if you simplify this, this is going to end up being $8,405. So compare this to what we had in the previous example. It's $5 more when we are compounding more times per year. So it turns out that we don't always just compound at the end of 1 year. We could compound quarterly, or we could compound monthly, or we could compound 2 times per month. So let's see what that looks like in a more general sense. If interest is compounded n times per year at an annual interest rate r, then after t years, an initial amount p grows to p times 1 plus r over n, all raised to the nt power, or n times t power. So example 8 says a total of $12,000 is invested at an annual interest rate of 9%. Find the balance after 5 years if it is compounded quarterly. So quarterly is another way of saying 4 times per year. And that's also equivalent to saying n equals 4, because remember, n times per year, so we're doing 4 times per year. So if I wanted to come up with a function, I'm just going to maybe call this f of t. So f of t is equal to p times 1 plus our interest rate over the number of times per year we're compounding to the exponent of n times t. Let's go ahead and fill in those values. Our principal amount of money here is $12,000. That's how much we're starting with. Our interest rate as a decimal is 0.09. And then I'm dividing this by 4 because that's our n value in this case. And then I have 4 times the power of t. And t in this example, t represents the number of years that pass. So now that I've come up with this general formula, I can use this to evaluate f of 5 because I want to find the balance after 5 years. So by plugging in 5, we have 12,000 times 1 plus 0.09 over 4 to the power of 4 times 5. And if you are throwing this into a calculator, after rounding to the nearest cent, you should find that this comes out to $18,726.11. So if you have this interest rate, the starting amount of $12,000, and you are compounding quarterly, then after 5 years, you'll have this amount of money in your bank account. Part B wants to make us do the same calculation, but now we're compounding monthly. So f of t is going to equal 12,000, our principal amount, times 1 plus our interest rate, 9%, or 0.09 as a decimal. And compounding monthly means that the number of times per year that we're compounding is 12. So our n value is 12 in this case. And now we want to, just like last time, evaluate f of 5. And so we'd have 12,000 times 1 plus 0.09 over 12 to the power of 12 times 5. And if you throw this into your calculator, this is going to end up rounding to $18,788.17. And one thing that you can do is, because we're compounding more times per year in Part B than we are in Part A, we would have expected to have gotten a larger number from Part A, which we did. So in Part B, we got a larger number. So in that sense, our answer makes sense, at least compared to Part A. So there's our final answer for example 8. Example 9 says, in 1986, a nuclear reactor accident occurred in Chernobyl, in what was then the Soviet Union, now modern-day Ukraine. One of the highly toxic chemicals that spread because of the explosion was plutonium. The government evacuated the city and the surrounding areas. Consider the model P equals 10 times 1/2 to the power of T over 24,100, which represents the amount of plutonium P from an initial amount of 10 pounds after T years. We can see from the function that the half-life of plutonium is 24,100 years. That is, after 24,100 years, half of the original amount will remain. How much of the 10 pounds will remain in the year 3000? So if we are starting in 1986 and we are looking for the year 3000, that means that 1,014 years will have elapsed. And we need to know that so that we know what time period to plug into our function that we create. So let's create our function, or actually we are given the function. So P of t is equal to 10 times 1/2 to the power of t over 24,100. So if we wanted to evaluate P of 1014, we would plug that in and replace that for t. If you throw that into your calculator, that ends up being about 9.713 pounds. So after 1,014 years, if we're starting out with 10 pounds, then after that time period, it will only have decreased to 9.713 pounds of plutonium. Part B says, how much time will it take for 2.5 pounds of the plutonium to remain? So if I were to make a table, and my input was the number of years, and then my output was the amount of plutonium in pounds, then the starting amount, we have 10 pounds. Then after 24,000, since that's the half-life, after 24,100 years, then that would get cut in half and we would have 5 pounds. After another 24,100 years, so that would put us at 48,200, then we would be left with 2.5 pounds. So we didn't really have to create a formula for this or use the formula. We can see that it just needs to get cut in half 2 times, and that happens after 2 half-lives. So to answer part B, 2.5 pounds will remain after 48,200 years. Now, part C says how much time will it take for 2 pounds of plutonium to remain? And the issue is if I wanted to use this same idea, if I cut 2.5 in half, that would leave me with 1.25. And the next half-life or time period would be 72,300. So 2 pounds falls somewhere in here, and that means that the number of years it would take would be somewhere between 48,200 years and 72,300 years. And guessing would probably not be the best way of going about that, since they have a difference of about 24,000 years, and that would not be the most accurate way of going about doing this. So there's a couple of things we can do. Let's go back to working with the function. So we're in part C right now, and we have p equals 10 times 1/2 to the power of t divided by 24,100. So in any other situation, what we do is p represents the amount of plutonium, and we want this to equal 2. And so in this equation now, what we're doing is we're trying to solve for t. And at this point in time, the only thing that we could really do in order to get closer to algebraically solving for t is taking this equation and dividing both sides by 10. But I'm just going to leave it as is for right now. We have these two equations. So really at this point, unless we have further tools, the best way we have about solving this equation is using some kind of graphing technology. Because what we can do is we can graph this function, which is just a constant function, and we can graph this function and see where these two functions intersect. So let's go ahead and do that using a graphing utility. All right, so I'm using the online graphing utility that's free called Desmos. Desmos is a free online graphing calculator. So I've gone ahead and I've plugged in my two functions. Unfortunately, right now my window's not very good, so I'm going to go ahead and click this little toolbar wrench in the top right corner and change my window. So my x value probably needs to be a lot larger. And earlier we said that it was going to be basically between 48 and 72,000. So maybe I'll make this like 75,000. So now I get a better view. Also, in terms of my y-axis, I don't really need negative y values, since the smallest amount, if everything were to disappear, would be 0. So maybe I'll make this 0. And Desmos is really cool because you have these two curves that are graphed, and if you kind of hover over where they intersect, I'm going to zoom in, and then if you kind of hover over it, it'll give you the ordered pair where those two things intersect. So what this tells us right now is after about 55,958 years, 2 pounds of plutonium will remain. So again, using graphing technology, we found that the answer to part C, we will have 2 pounds of plutonium left after about 55,958 years. And that concludes example 9. Example 10 says you receive a new job with a starting salary of $50,000 per year. Your company offers you two different salary schedules. In offer A, you receive a salary increase of $2,000 every year. In offer B, you receive a 3.5% salary increase every year. Which offer do you take? Explain. So offer A, if it's not clear, is going to be modeled by a linear function since we have a slope of $2,000 per year. Offer B is modeled by an exponential function because you're receiving an increase of 3.5% every year. So that means that our common ratio, or our growth factor, is going to be 1 plus 3.5%, which would be 1 plus 0.035. So that means that our growth factor would be 1.035 in offer B. So I'm going to make a table to kind of see if we can weigh our options that way. All right, so in the first column, we have the number of years, which is our input value x. And in column A, we have f of x, which is from the offer A, and then offer B, in that column we have g of x, and we have those output values. So as we can see, the starting year in both scenarios, we have $50,000. And at the end of 3 years, you'll be making more money if you take up offer A. But really, we probably want to know, is there a point where that will change? Because if I were to graph this, here this would represent the number of years, and then this would represent salary. One of these, they're both starting at $50,000. One of them is a linear function, and one of them is an exponential function, which means it's going to look something like that. And so at some point, these are going to intersect, which is why it's important for us to come up with function formulas. So the function formula for f of x, because this is a linear function, is going to be 2000x. That's our slope. Our slope is 2000. And then our starting amount is 50,000. So there's our linear function. And then g of x is equal to, we have the starting amount of 50,000, and then our common ratio, or our growth factor, is 1.035, and then this is going to be raised to the x power. So really what we want to do in order to figure out where these intersect and to get this x value, this mysterious x value, is we want to set these two things equal to each other. So I'm going to take these two functions and I'm going to set them equal to each other. And our goal is to figure out what x is. And again, at this point in time, we don't have the tools to solve this algebraically. So I'm going to go ahead and have us rely on Desmos again, or some kind of graphing technology. So let's throw this into Desmos. All right, so we can see that I've entered in my two functions right here, and then on the settings, we could see that I changed my window. My x values, the x min, I changed it to 0. My x max, I changed it to 40 because I do not want to be working for more than 40 years. Really, I don't want to be working for more than like tomorrow, but that's life, it's tough. And our y-axis, the smallest amount of money is maybe 0. And then our max salary is maybe like $100,000 per year. So we can see, like I said, our blue graph represents our exponential function, and that's offer B, and then offer A is our linear function. So I can kind of hover over. I think it wants me to zoom in a little bit to see where they intersect. So I'm going to zoom in a little bit. And then here, it tells us that after about 8.5 years, both plans will be the same at about $67,112. And then any point after that, our option B would be a better offer. So let's go back and look at that. So here, this point of intersection, the x value was about 8.556. And then the y value, here our salary, was about 67,100, and let's round it to the nearest dollar, so it'd be $113. So really the answer to this question, which offer should you take, is kind of dependent on how long you might stay at this job. So if you were to spend less than, let's just round it to 8.6 years at this job, offer A is better. And alternatively, if you were to spend more than 8.6 years at this job, then offer B, the exponential offer, would be the better offer. So that concludes example 10.